All right. So chapter 13, this is a tough chapter, but there's not a lot that's new. All right. So really, this chapter is going to be about just sort of me exposing you to a bunch of problems, and you guys kind of monkeying with different ideas about torque and net force and problem solving. All right. A lot of these boil down to systems of equations. Most of the problems are going to have three equations and often three unknowns. Um, so I'm going to kind of hit here with the basics and give you guys time in class to work on this stuff, and we'll kind of troubleshoot as we go through it. All right. So here we go. So this the first thing here is just kind of some definition stuff. So we've already learned about center of mass, right? Average position of mass. An object's center of gravity is an average object's average position of weight. So for most objects, an object's center of gravity and center of mass are basically the same. But since, for example, the Earth's gravitational field gets weaker as you get farther from the Earth, very tall objects will have a center of gravity which is slightly below its center of mass. What does that mean in English? We haven't really learned about fields yet, right? But like, so imagine a very large tower like the Empire State Building, right? So here's the Earth, here is giant tower, all right? Empire State Building, right? Let's suppose for simplicity that it is, in fact, uniform. Okay. Well, if that's the case, then what that means is if it's uniform, then your center of mass is going to be at the geometric center, right? Okay. But let's consider weight. Remember, one of the things we learned last year, and we'll revisit this again next chapter in chapter 14, but remember, force of gravity is equal to G times the mass of one particle times the mass of the other particle divided by the distance between their centers squared, right? So the idea is this tower is so big that if you treat the two halves as having equal mass, what's going to happen is this bottom half is closer to the center of the Earth than the top half, right? And so what happens is the bottom half, even though they have the same mass, the bottom half technically weighs more, all right? And so what that means is the average position of weight is a little bit lower because the bottom half weighs more, even though it has the same mass. Okay, but that's only for very, 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 very large objects. So for all intents and purposes, that might be a multiple choice question on an AP exam. But in terms of problem solving, we're going to always just assume that these two guys occur at the same point. Okay, so. All right, there are a couple types of equilibrium, right? So when you talk about equilibrium, you're saying that the object has a net force of 0 and a net torque of 0, okay? So usually we assume it's at rest. I suppose theoretically it could be moving at a constant velocity or rotating at a constant angular velocity, okay? There are three types of equilibrium. Okay, if tipping the object or slightly bumping the object raises the center of mass, that's called stable equilibrium. Okay, because the idea is when you tip an object, if you raise the center of gravity, gravity is going to want to correct it and lower that center of mass. Okay, so here's the simplest example down here. All right, here are the three types of equilibrium. All right, so this bottom drawing, I've never heard these terms before. They call it static here. So this is stable equilibrium. I guess apparently sometimes called static equilibrium. This is stable equilibrium because if you lift the ball, if you nudge the ball, it's going to go up a little bit and gravity is going to correct it. So that's called stable equilibrium. All right, this one, which they have here called dynamic, I've usually heard called unstable equilibrium. This is unstable because here, if you nudge it a little bit, you're lowering the center of gravity, and gravity is just going to make things worse, and it's going to roll down the hill, right? Okay. And then there's neutral equilibrium, where nudging the object doesn't raise or lower the center of gravity. Okay. Another example would be this. If you take a meter stick, you balance it on one end, that's unstable equilibrium, right? Because if you nudge it, the center of gravity is going to work against you. Whereas if you take that same meter stick and you pivot it from the top, now if you nudge it, a little nudge will raise your center of gravity, so that's stable. So this is unstable, and this is stable. All right. If you simply pivot it at the middle, if you drill a hole and pivot it right at the middle, that would be stable equilibrium, right? Because then tipping it, you're not changing the center of gravity at all. Okay. The clown in my room, the reason that clown balances is because it is in stable equilibrium. What clown am I talking about? There's that clown on a bicycle, right? So let me see. Here's the clown. He's got a little clown hat. Okay, and he's got this pole, and the pole kind of bends down, right? And he's on a unicycle or whatever, right? Okay. But so the idea is, because of these little masses here, the clown is on this tightrope, right? That kind of runs like that, right? Okay. But the idea is, because of these masses here, the center of mass of the clown and his bar is actually down here. So when he tips a little bit, your center of mass goes up. Gravity doesn't want that to happen, so gravity corrects the clown every time you tip him. Okay? So that is an example of stable equilibrium. All right? So, all right. So everything here, this is all review. We've reviewed it this year. It's all about torque, right? To produce a torque, you need a lever arm and a force, and this angle matters. Okay? These angles are going to be super important in this chapter. Remember that there are two ways of calculating torque. You can do torque equals, well, you can do FD sine theta, right? All right. You can calculate the component of the force, which is perpendicular to the lever arm, or you can calculate the component of the lever arm, which is perpendicular to the force. All right. We're going to be using all three of these as we go through this chapter, all right? So just try to be flexible with how you think about torque, okay? Because they'll come up, all right? So I'm not going to spend time on this. We've talked about it. If you want, you can go back and watch videos from earlier this year, or definitely honors videos. Has all of this stuff. Which has just made me realize I need to keep my website up. Sorry, random thought for myself. Okay. All right. So this is an example we did in honors last year. You've got a teeter-totter. The board has mass. You're given the length. Blah 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 blah. You're trying to figure out where Roy has to sit to balance the board. All right. Please remember, if you're looking for if there's an unknown distance, my strong recommendation is you choose a pivot point at a known point, usually at the end of the board, okay? So in this problem, the idea is you've got this, this teeter-totter, and, Sally's at one end, and the question is, where does Roy go in order to balance it? And since you've got an unknown distance, my recommendation would be choose this end point as your pivot point, all right? Now, if you're looking at this and you're like, what is he talking about? Stop the video right now and go back and watch the honors video on equilibrium, okay? I don't remember what chapter it is, but you can go back and look at the website, all right? Please, please do this, all right? Because if you don't know how to do this, you're going to struggle for the rest of this video. It will be worth the 20 minutes it takes to go back and watch that old video, okay? All right, so I am going to now assume that you've done that, and I'm going to move on, all right? Now, so if an object is in equilibrium, we've got three useful problem-solving facts. All right, so first of all, the net force has to be zero, right? So that the linear velocity and the momentum are constant. Why do I say three facts? Well, really, frequently we're dealing with two dimensions. So when I say that the net force is zero, that's true both horizontally and vertically, all right? So we've got these two equations to work with. We know that our net force horizontally is zero. We know that our net force vertically is zero, all right? And then finally, we also know that our net torque is zero. And really, this gives us kind of an infinite number of equations, right? Because your net torque is zero about any pivot point, all right? Okay, now, please, please, please remember that your choice of pivot points can either make or break your solution, all right? So you really need to be strategic about where you choose that pivot point in terms of problem solving, all right? So let's do an example. I think I've got two examples here lined up for you. And then honestly, it's just about kind of digging in and trying the problems, okay? Yeah, so here we go. All right, so here we've got a 6-meter long board. It's propped up to form a ramp onto a platform that's 2.5 meters tall. The top of the board, like the top end of the board has a mass of 30 kilograms. Oops, I forgot to put units in here, 30 kilograms. The top of the board extends 1 meter past the corner of the platform. So if the corner of the platform is frictionless, then find the smallest coefficient of static friction on the floor, which will prevent the board from slipping. All right, so this is the sort of thing where I would give you a drawing, if this was a test question or a homework problem or something. So here's the deal. So you've got the floor, you've got this 2.5 meter tall platform. So this, 2.5 meters. All right, now we're going to take a 6-meter long board and put it on here. But the top of the board extends past the end of the platform, so it's going to look something like this. So here's the board, like that, all right? And so the idea is this whole thing is 6 meters. This little chunk here is 1 meter, which means that this chunk here is 5 meters. Okay? Now, let's see. It doesn't explicitly say it. I should have said a uniform 6-meter board is propped up, okay? So since it's 6 meters long, that means that our center of mass is going to be at the geometric center, which will be 3 meters up the ramp, okay? And we know that, go brain, we know that the mass is 30 kilograms, so I can go ahead and put in my force of gravity. 30 times 9.8 is 294 newtons. Okay, so what other forces are there? Well, the floor is supporting it over here, right? So there's a normal force here. Okay. Let's see, I'm going to kind of clean up this drawing a little bit here because it's getting cluttered. Okay. So there's a normal force there holding it up, right? The corner's also doing something. Now, this is not at all obvious. But I am telling you now, when you've got a corner contact point like this, the normal force is perpendicular to the surface, okay? So there's your normal force, but I can't call it normal force because I've already called this green one normal force. So I'm going to call that FC as in force of corner, okay? So it says if the corner of the platform is frictionless, then find the smallest coefficient of friction on the floor. So there's got to be some friction. I'm out of colors. There's got to be some friction down here, right? Because if this point here is frictionless, does it make some sense? I don't know why I'm asking, you can't answer, but hopefully it makes some sense that if this is frictionless, the board is going to kind of want to slide down, right? It's going to want to kind of slide this way, right? And so the friction is going to prevent that, right? Furthermore, you can see, notice this force of the corner, it's got, a horizontal component that's pushing that way, right? That's what's going to cause it to want to slide, okay? And so therefore, we have to have, I guess I'm just going to do it in green, a force of friction over here to cancel out the horizontal component of that corner force, okay? So we've got 3 unknown forces here, don't we? We don't know the force of the corner, we don't know the normal force from the floor, and we don't know our force of static friction, okay? All right, so here's what I do know. I know that my net force vertically has to be 0. Ugh. I know that my net force horizontally has got to be 0, but this doesn't help much, right? Because that corner force has a vertical component, the normal force is vertical, so there's 2 unknowns there. Horizontally, it doesn't help me any because I don't know my friction or the horizontal component of my friction. All right, so we're going to start with torque. All right, so here's the deal. We know that our net torque has to be 0. We're going to do this in black. So here we go. Net torque has got to be 0. Now remember, we want to choose our pivot point strategically. Okay? A strategic choice of pivot points will reduce the number of variables you have in your equation. So I could theoretically choose my pivot point up here at the corner. But the problem is then I'm going to have a torque provided by this normal force and a torque provided by static friction, right? And I don't know either of those forces, so I would have 2 unknown forces. So maybe we can use systems and try to solve it, but I'm not ready to do that yet, all right? Choosing gravity is even, if we choose this as our pivot point, choose the center of mass as our pivot point, that's even worse, because then we have 3 unknown torques. But hopefully you are noticing, if I choose this contact point here at the floor, if I call that my pivot point, then the torque provided by the normal force and the torque provided by friction are going to be 0. Okay, so that is going to be my pivot point. All right, so what that means then is my net torque is 0. That net torque is equal to the torque provided by the normal force, which is going to be 0, plus the torque provided by our static friction, which is going to be 0, plus the torque provided by gravity, plus the torque provided by that corner. Those all have to add up to 0. So here we go. 0 equals, let's just cross these guys out. Those are both 0, right? Okay, so our torque provided by gravity. Well, that's, let's see. There's a thing that I haven't done yet. There is a triangle here. I'm going to check it out. There's a triangle here, right? This side is 2.5. This side is 5. That means that this angle here must be 30 degrees, right? Okay, so you can SOHCAHTOA all of that, figure that all out. Let's get rid of the yellow. Let's draw this in here. This is 30 degrees. So that means then that this angle here must be 60 degrees, right? Just because it's a 30, 60, 90 triangle. Okay, so let's biggen this again. Here we go. So our torque from gravity should be the force of gravity. We'll do that in red. 294 newtons times our lever arm. Well, this force of gravity is 3 meters away from my chosen pivot point, times the sine of the angle between the lever arm and the force. So times the sine of 60 degrees, okay? Plus the torque provided by the corner. That's our unknown. So let's see, the lever arm for our corner is 5 meters, right? 6 meters minus the 1 that's hanging over. So it looks like force of corner times 5. And, oh good, remember, that corner, the force provided by the corner is perpendicular to your surface. So that's just sine of 90, right? Which is 1, right? So we don't need to worry about that, all right? Now let's check our signs. It looks to me like gravity is going to produce a negative torque, right? Okay, so solve this, and you will discover that the force of the corner is a number that I've written on a piece of paper right here. It turns out to be 152.77 newtons. All right, cool. So now we know the force of the corner. So now I feel like we can go back to our forces, all right? So that force has 2 components, right? So let's see. So there's a triangle here. I'm going to highlight this again. So there's a triangle here. So there's that, right? So there's an x component and a y component. And it turns out that if you kind of draw in a horizontal line here, turns out this is going to be 30 degrees, which means that this angle here is 60 degrees. Okay? So here's the force of the corner, 152.77. This is 60 degrees. So the force of the corner in the x direction is that times cosine of 30, which is negative 76.38 newtons. And the force of the corner in the y direction turns out to be positive 132.3 newtons. Okay? Okay, so now what I'm going to do is let's set up 2 equations. We know that our net force in the x direction has got to be 0. So that means that, let's see, the only x forces are the force from the corner in the x direction plus the force of friction, static. Those have got to add up to 0. So you've got negative 76.38 plus the force of friction static equals 0. Oh, my force of friction static is going to be positive 76.38 newtons, right? to prevent the board from sliding to the left. Okay. And then similarly, we can do this. We know that our net force in the y direction has also got to be 0. So 0 equals, let's see, net force in the y direction. Well, that's normal force at the floor plus gravity plus the force from the corner in the y direction. So 0 equals normal force minus 294 from gravity. Notice it's a negative force because it's down. Force from the corner vertically is the 132.3. Solve this. Normal force turns out to be 161.7 newtons. And so now we can go, oh, force of static friction is coefficient times normal force. 76.38 equals coefficient times 161.7. And your coefficient turns out to be 0.47. Holy moly, there's a lot going on there, right? Okay, so a lot of this is just kind of trial and error. Sometimes you got to use the net force equations first. Sometimes you got to use the torque equations. Honestly, usually you got to use the torque equations because you have the addition of choosing your pivot point, you're very frequently able to sort of not cancel out forces, but the torque provided by those forces is 0, okay? All right, let's do one last example. So in that one we had to find unknown forces, but we knew all of our distances. What happens if we don't know a distance? Okay, so let's see. I recycled a drawing. All right, so we've got this drawing. I didn't write down the text for the problem. Here's what we're going to try to do. All right, here's our goal. Let's suppose that the tension maximum on this cable here, it's got to be less than or equal to 300 newtons. Okay, and so the question then, let's suppose that this whole beam has a length of, let's call it just L. All right, so my question is, where do we need to hang this guy? We got to move it somewhere. Obviously, you can't move it farther to the right. Never mind, just drew that other arrow there. But where do we need to move it to ensure that we don't break the cable? Okay, so again, we've got an unknown distance, right? So this is what I was talking about at the start of the video. So what you want to do is choose a pivot point that A, minimizes forces, B, make sure that it's at a point that is a known point, okay? So in other words, don't choose your pivot point to be, where the 400 Newton goes, because we don't know where the 400 Newtons goes. All right, so let's see. So let's think about what our free body diagram is going to look like. I'm going to erase all this stuff. I'll just make a note here. Okay, so what do we got? So we've got tension. We're going to set that equal to 300 newtons. We've got force of gravity, 400 newtons. All right. And then this hinge is actually providing some forces, right? It's got to be holding it up. So the force of the hinge vertically, and since the tension is pulling to the left, the hinge has to be pulling to the right, or pushing to the right, I guess it would be, right? Okay, so those all have to add up to 0, okay? But hopefully you can see we can kind of choose our pivot point, much like we did last time. We're going to choose this to be our pivot point, right? So the net torque about the hinge has got to be 0. So 0 equals, well, our net torque is going to be, well, these two guys don't provide any torque, so it's just the torque from gravity plus the torque from tension, right? So 0 equals, let's see, torque from gravity is going to be the force of gravity, 400, times, well, let's see, my lever arm is this. That's my unknown, right? So we can call that x times the sine of this angle, which has got to be 70 degrees, right? Plus the torque from tension. So our maximum tension is 300 times, we decided that the length of this thing was L, times the sine of, well, let's see, the drawing is now all cluttered. let's see, so if this is 20, this must be 20, which means that this is 65, right? 20 plus 65, or 20 plus 45, rather. Okay, and those have got to equal 0. Let's see. The weight is going to have a negative torque, right? Okay, so solve that. So you get 400 sine 70 times x equals 300 sine 65 times L. So you get 375.8x equals 271.9 L. So x turns out to be 0.72 L. So 72% of the way out the beam is where you got to hang the mass. Okay? So that's kind of it. Like I say, it really is just going to be about digging into the problems and trying them, all right? So that is that. I'm hungry, you guys. I'm going to go get a sandwich.